So to get started, we want to figure out how to take the determinant of a larger matrix and transform it into a determinant of a smaller matrix, because ideally that's going to make our lives a lot easier. Looks like there's a missing image in this diagram, so I'm going to switch over to the other copy of the textbook real quick here. This is G2. Okay, so here is our first activity, and I'll just want to talk through this activity together with everyone here. So here is a matrix 1, 1, 0, 1, 3, 1, 0, 0, 1. And here is the image, a sketch of the image of the unit cube. So it's what you get when you transform the three standard basis vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, with the linear transformation of which this is the standard matrix. And so, not surprisingly, the images of those standard basis vectors are just the three columns of this matrix. So 1, 1, 0, this vector right here is the image of the first standard basis vector. 1, 3, 0 is the image of the second standard basis vector, and then 0, 1, 1 is the image of the third standard basis vector. And so the determinant of this matrix is going to be the signed volume of this parallelepiped. And so to find it, we can find the volume of any parallelepiped by finding the area of its base and multiplying it by its perpendicular height. Right, this is a standard technique in polytope geometry. So if I want to know what the volume of this is, that's going to be equal to the determinant of this matrix, I can find the area of this parallelogram base that's been shaded here and multiply it by the perpendicular height. But here, the perpendicular height of this particular parallelepiped happens to just be 1. And we know that because this bottom face, the red shaded face, actually resides in the xy plane of three-dimensional space. And its parallel opposite face, which is up here on top, actually lies in the plane z equals 1. It is a parallelepiped after all, and so it's made of three pairs of parallel sides. And so that means in particular that the vertical distance between those two planes is the same thing as the orthogonal height of this parallelepiped. I'm using a lot of geometry terms today, so a little bit of an apology, but maybe it's more of a sorry, not sorry for that. So the height of this parallelepiped is 1. So the question that I want us to think about for a moment is just how would I find the volume? Like, what would this volume be equal to? And how would it be related to the determinants of one of these 2x2 matrices? Step 1 is to recognize that the volume of this parallelepiped, because the height is just equal to 1, the volume and the area of that red shaded base are going to be the same number, right? Because the volume is the area of the base times the height, but the height is equal to 1. Right? So whatever determinant that we're looking for is going to give us the area of this red parallelogram. So which of these four determinants that are the options is going to give us the area of that red parallelogram? Yeah, so it's the first one. It's the first option, 1, 1, 1, 3, right? And that determinant, so I'm going to mark this up here, that determinant tells me the area of the parallelogram that's determined in the xy plane by the vectors 1, 1 and 1, 3 in the xy plane. But after all, that area in the xy plane is exactly this red shaded area, because that red shaded parallelogram actually resides in the xy plane. And so if we just sort of, and this is actually an important step here, so I want to draw a little bit of attention to it. If we just sort of forget about the z coordinates of those vectors, we actually don't lose anything important. Nothing of value gets lost when we forget about the z coordinates and just focus on the x and the y coordinates. So this is a dimension reduction technique, which anytime you hear dimension reduction, you should always run in the direction of that thing. It's like one of the most useful techniques in statistical analysis, for example, of multivariate data sets is dimension reduction. Anytime you can take a larger dimensionality problem and reduce it to a smaller dimensionality problem, you are doing good work, because you're going to make your life a whole lot easier. So what then I'd like to notice, and yeah, we're focusing on the xy plane here, and let's look back at the original matrix and see if we can figure out what it is in the original matrix that's going to tell me that we're focusing only on the xy plane, why it's okay in this example to focus only on the xy plane. So let me pose that question to you. So the first thing we notice is that the determinant that we ended up writing down as our answer, is the determinant of this 2 by 2, what we call a block. It's a submatrix of this matrix. So here is the 2 by 2 block, 1, 1, 1, 3, whose determinant actually does give us the the determinant of the larger matrix. So that's important thing number one. That tells us what we should be focusing on. And then
And
the
then
flip
also
side is
because we have zeros in the column and the row.
we have zeros in, well, we actually don't have enough zeros in this column to really get away with what you say. But I do agree that we have zeros literally everywhere in the third row of this matrix, with the exception of that third entry. So these zeros that are underneath that matrix seem important, right? It's telling me that whatever is happening with the volume of this box, I can figure out what's happening with the volume of this box by focusing just on the 2 by 2 block, because there's only zeros underneath that 2 by 2 block. Might be another way to think about what we're seeing here. So these are the kinds of ideas that we want to try and pull on these threads a little bit and see how to generalize. How can we figure out, if you give me a big gigantic matrix, how should I figure out what I should be focusing on, and what I'm going to be able to throw away? Because here, this matrix happens to have zeros in strategic locations that are going to be the reason that we can throw away and ignore the z component. But most matrices probably don't have a lot of zeros floating around, and so we should try to figure out what would happen in those more general cases too.